Hey, good time of day, everyone, and welcome to a new MLIR open meeting. Today, we have the pleasure of having Sean and Anush presenting about the Torch MLIR project, formerly known as npcomp. So, Sean, Anush, take it away.
Hey, folks. I'm Sean, and just to give a little bit of background on who's speaking. So I'm here on behalf of the Erie team at Google, especially where we've been working on sort of a lot of front-end related work. You may have seen us working on TOSA stuff, for example, Rob and Natasha. And so the background here is, we started the Torch MLIR project as npcomp because there really wasn't any MLIR interop with Python more broadly, and we kind of grew it into Torch MLIR and deleted all the things that were not part of that, which ended up being sort of experimental and not quite baked. Speaking as the Erie team, we need a good PyTorch front end, and everyone does, and we really are committed to keeping this independent from Erie, for example. Actually, at some point we had some mentions of Erie in the code base, and we went and scrubbed them, and we intend to keep that type of layering up. So currently it's me and Yi actively working on the project from our side, and Stella sort of founded the project and did a whole bunch of stuff. And so hopefully we're on track to having a nice ecosystem here of upstream adjacent or kind of not vendor, not super frameworky interactions with the different fronts. All right, Anush.
Yep. Thanks, Sean. So just a background about us. I'm talking on behalf of the Nod.ai team here. We've been working on MLIR for almost 2 years now, or since the inception, and we do we've helped customers from edge devices all the way to supercomputer kind of deployments. But everywhere we go, we've been seeing one particular problem, and that's just everyone's implementing something from PyTorch to MLIR, and it's just been a pain point. It's everyone's re-implementing a C++ front end for an LLVM backend, and I'll talk about that in a little more detail. But just a little bit about more about what we do. So we enable silicon companies with their silicon bring up and just integration with MLIR ecosystem, and we complement your internal teams. So in some cases we provide just code gen search, kind of like TVM answer does, but for MLIR. And we've been able to outperform TVM answer and we have benchmarks for that, etc. So the company itself has been around for 8 years. We started with IoT, and we kind of found our way towards AI performance and efficiency about 4 years ago. We did a lot of low precision training then on FPGAs, and then we've kind of settled in on this ML systems layer now, and just kind of enable MLIR for customers, and with varying complexity from small edge devices to systolic arrays, etc. So like I mentioned, if you build AI silicon, you should talk to us. A lot of you on the call, I recognize we work with you, so thank you for your support. And also as a pitch for if you're interested in ML, CS, math, and hardware, let us know. We're hiring. We have more customers than we can support right now, and so growth is the team is the limiting factor. So I was at Google prior to this about 8 years ago, and I came in through an acquisition, and we did a lot of the Chrome OS build out with ARM GPUs back in the day in 2010, 2011. Our CTO Harsh, he's on the call. He was in Kitty Hawk building flying cars. We have a bunch of people contributing actively. We have about 4 people right now: Ramiro, George, Dan, Stan. And we have about 4 more people that should be coming up in the next few days, to join this group. They're working on something else right now. But overall, we're very committed to this. We just think every customer we go in for hardware enablement, we see like a hodgepodge of like something that that should just be like really easy and kind of like lift all the boats in the sea. So that's where we are. So let's go to the next slide, Sean. And here's a little outline of what we're going to talk about. We'll do like the what, why, and the roadmap, the Torch dialect, the front ends, the back ends, demo. After the what, why roadmap, I'll hand it off to Sean, and he'll get into like the more technical details of it. Cool. Next slide. Yeah. So what is Torch MLIR? It's a confluence of 2 large ecosystems, PyTorch and LLVM MLIR. And can anyone guess which place this is? Okay, image search will help, I think. But this is in Geneva. It's 2 rivers that are a confluence of 2. The Rhone and RV, I think. So those are the 2 rivers. And so you can think of us like, if you see that little boat over there, we're like the little tug team that big ships, when they come in there, you have like the little tugboat that guides you through the intersection of like complex areas. That's what Nod.ai does today. We kind of have been enabling AI chip companies to navigate the kind of like the intersection of these 2 big ecosystems. And the goal of this is that can we bubble it up so that it's less of what we do, and everyone focuses on moving like the industry forward and not on like recreating a PyTorch to MLIR lowering. Let's go to the next slide. So this is a nutshell. If you want like a high level and this kind of gives you enough understanding without getting into the very gory technical details of how we're mapping tensors, etc. But at the top we have PyTorch. Obviously, everyone's aware of like the TorchScript interface, which is kind of a very stable interface. There's an up-and-coming interface called TorchFX for functional transformations, etc. And then there's also something called Lazy Tensor. That's more, it's still early stage, but it gets to kind of recreating what Torch XLA did, but in a more standard fashion. And what we plan to do is let silicon vendors not worry about TorchScript, TorchFX, Lazy Tensor. We kind of like bring it to the Torch dialect. We take on that that burden, and obviously we want everyone to chime in. There's like 115 people on the call. Obviously, there's a lot of interest in this, so we'd like to get as much community support. Stand this up as a platform neutral bridge that everyone gets to use, and it helps bidirectional commerce. So the lowering from there gets into the 3 pieces that we have, and Sean's going to get into the details of each one of these chunks. TorchScript is our primary path right now, and then we have an example for FX-MLIR converter because TorchFX itself is in flux, but we're tracking it very closely. LTC-MLIR plugin or LTC TS plugin is something that we also have a working prototype of, and we're actively contributing to upstream to make sure those paths are all solid. But bottom line is, as it matures, we want silicon vendors to just focus on the Torch MLIR dialect and below, and we want to give you CTS like compatibility test suites, benchmarks, etc. So you focus on what you bring to the table. If it's whatever it is that that you think is the core value of your silicon or your cluster or your solution, you can focus on that and not worry about like how you do a PyTorch to MLIR lowering, and you can just contribute if there's anything that isn't covered. But over time, we expect this to like quickly ramp up, and Sean's going to show you some demos with like ResNet, and we have BERT on the way, and Mascar CNN, and so we're going to have like validated models. So if there are specific models that you would like to see, we're all welcoming all your input and feedback. One thing that we have here is we want this project to be completely independent of anything else. So the only dependency is PyTorch and MLIR, LLVM MLIR. So you have a full reference MLIR CPU runner. So you can do a CPU, invocation of, ResNet or whatever you want to test. The idea is that, we want this to be a truly like neutral, no man's land kind of area. And it's fully self-contained. So any customer that wants to, implement a CPU backend, a GPU backend, or an accelerator just takes off from there. And there's no other, tentacles of things coming into Torch MLIR. So we'll strive to keep that kind of like encapsulation so that it's easy to, upstream parts into PyTorch, upstream parts into MLIR and LLVM. Cool. Any questions so far before we go to the next slide?
Are you going to talk about, for example, like inferencing and?
Yes. So it's a good point. So right now, the goal is both inferencing and training. So we actually are, we want this to be a full-scale solution. The integration points with PyTorch and the path we choose down has some implications and some complications of like inferencing or training. The predominantly, the most tested path is the TorchScript inferencing path, which is on the left side. It says inference graphs over there. And then the least tested is the LTC MLIR plugin path, which is the training graphs. We have had some contributions, between like Xilinx had contributed an ACAP thing that, that the npcomp repository had that used to modify the Torch XLA, the backend to capture the entire training graph. But we're moving forward with the supported way of doing it, and so we've deprecated ACAP, and all training graphs will go through the LTC path, and we're hoping to mature both the plugin and the upstream as required. So that's a good question. Can TF be lowered to the Torch MLIR dialect? I don't know if you'd want to do it, but I think there are other intermediate things that you'd want, and Stella, Sean, you guys may have more context on it.
So technically you can do it if you want.
Sorry?
Yeah, I think the question is why you would want to exactly, but it's completely technically possible. They're basically both NumPy, I mean, roughly speaking.
Cool. And so, so our primary focus here is just on the Torch side, and I think Sean has some more slides that show, like, you can map it to MHLO, TOSA, other things lower down. So you could convert out from Torch MLIR. Once you cross that, that bridge and you're in MLIR land, you get all the benefits of like, pattern rewrites, and, it's just a pass that you're going to like support to go from one dialect to another or whatever you want. And that the cost you pay for that is even less compared to like actually plumbing into PyTorch and plumbing into TensorFlow. So we want to abstract that out.
Are you going to talk about ahead of time compilation?
Any of the what compilation? I'm sorry?
Sorry, ahead of time compilation.
Yes. So I think the in this path for training, we are going down the LTC path for ahead of time. It is AOT. The I think if you're asking about like the inverse of that, which is like where's eager mode, right? So I think that gets a little more tricky.
No, sorry to interrupt. My question, like especially in the inference, you want to have like ahead of time compilation, optimize the model, and kind of deploy it, versus in the training where you might be fine if you just do just in time compilation and lower graphs, compile them on the fly. This is kind of a follow-up for the inference. It's for how you're going to enable inferencing with this ahead of time compilation and optimizing the models and the weights and all these kind of things.
Yeah, I'll speak to that. I'll speak to that later. The Torch script inherently creates a standalone deployment artifact, so it is exactly what you want. It sounds like.
Okay, good. I'd love to hear that.
Cool.
There was a question on the chat also. I don't know if you addressed it.
Yeah.
About it's a bit unrelated, but it's about where does a vendor that would consume TensorFlow would fit in this picture.
Yeah, I think I answered that one. So that is the one that we can convert from Torch if we wanted to, but the TensorFlow dialect would be something equivalent, or TensorFlow or MHLO. I think Sean has some pictures on that will.
The short answer is yes, you can technically do it.
Yeah,
it just would be a lot of work.
How do you handle the thousands of ops that PyTorch supports? And
I'll get to that
in
in the next part of the presentation. So
Great.
Anush, let's power through the rest of Anush's part.
Yeah, we'll get to that. We'll hold that question. Okay, let's get to the next slide and yeah. So this is just kind of going into a little more detail. What is Torch MLIR? And like we've been talking about, it aims to centralize the PyTorch and MLIR interop code paths. And so downstream focuses the unique value of whatever you want to build, and not worry about PyTorch integration. And obviously, popular model hubs like Torch Vision, Hugging Face, NLP, etc. will work out the box. It's an LLVM incubator project. That's why you're here. We have made it dual licensed so that it can go up into contributions could go up to LLVM. It can go up to PyTorch with its BSD license. So we really want to move this as close as possible to upstream. And that's the link for where you can find us. And that's on Torch MLIR Discord too. And we do have an RFC pull request with PyTorch. We're waiting feedback on what the next steps are. Cool. Let's go to the next one. So why Torch MLIR? I think we've hinted to this along the way. It lets silicon vendors focus on their differentiation and their backend without the need to keep up with the frameworks. I'm sure some of you are still supporting TensorFlow 1.5 or 1.2 or 1.15 for some reason, especially like frozen graphs. And that bridge from that has been big to cross for silicon vendors, and trying to keep up with the latest PyTorch and TensorFlow for that matter. It has become I've seen half the compiler team of AI silicon companies spend time just trying to keep up with the frameworks. So if you sort the amount of people allocated to keeping up with the frameworks and actually doing what you have to do, it's 50% or more. Because by the time you get a BERT model through, you're it's exhausting. But I personally know of 5 custom implementations of PyTorch MLIR that shouldn't be that way, right? It's like writing a Clang C++ front end for every LLVM backend that you want to add. So we want to bring it out like Clang. You don't worry about the front end. Let the front end take care of what it has to do with C++, AST, whatever, and you implement an LLVM target backend and call it a day and optimize on that. And so similar to that, we're going for that so that we enable silicon vendors to just accelerate and deliver on their value prop and not worry about what PyTorch is doing this week or TensorFlow is doing next week. So there's a need. I think as of yesterday, there were we posted this a week ago on PyTorch Discord, and we are about 417 views, and 10 people have expressed support. But if you're interested, please go to that link there and just either anonymously or as part of your company, just be like, hey, this will be interesting, something like that, so that the PyTorch guys know that, hey, this is something that's interesting for silicon vendors. If there are 120 people that are interested in this, even if it's 10 companies, I think that gets on the PyTorch team's radar to say, hey, there are 10 companies that are going to be working on this anyway. So maybe they'll consider closer integration or enable us, etc. Cool. Let's go to the next slide. And so, what's the future? And you should guess where this image is if anyone can. But we're thinking of where the two ecosystems kind of merge, and it should give you the best example is the Clang example, right? The Clang C++ example. You just take that, you just go into lib targets backend, and bam, you enter, you implement your stuff, and you're up and running. So we want to get to that for ML workloads, And I think that'll help the industry kind of like, focus on what we can bring and what we can enable, like whether it's large model training, edge optimizations, etc. So we will continue doing validated models and op support, Hugging Face, Torch Vision, we talked about that. Anything else you guys are interested in, please do chime in, and open issues or PRs are welcome. And we want tighter integration with PyTorch. We want to solidify the lazy tensor core path, the TorchFX path. And we don't know what the evolution of those paths would be, but whatever it is, we want to have first-class support. And having 120 people behind one effort will avoid everyone trying to figure out what is lazy tensor core doing, what is TorchFX doing, what's TorchScript doing. So this way we have a clear conduit that's just free-flowing. And like we discussed, first-class training and inference support. One thing that I'm very excited about is like we want to build a compatibility test suite for silicon vendors. It should be push-button qualification for all its challenges. For those of you who worked with Android CTS, kind of that level of compatibility, but address some of the issues with it. But we want it to be open source, and you just run this compatibility test suite, and that Hugging Face's latest model is going to just run, right? And the ops are supported, and it's going to be most performant. And then your engineers start from there. You can make small repro test cases. Bringing up your silicon becomes easy. You divvy up and say, hey, these ops this way, and don't worry about what Hugging Face's latest model is, because the CTS will be updated. Benchmarks, obviously, to help you understand where you are with respect to the latest CPU, GPU implementations. Obviously, accelerators are like more siloed, so we won't be able to share that unless they're publicly available. So as much as publicly available CPU, GPU information, we can roll into benchmarks. And then we'll add some example dialects. So we want to make it even easier for you to say, hey, what if I had some fancy interconnect mechanism, or if I had a 3D grid of processing elements, or if like I had optical compute or compute optics or whatever it is, we want to add example dialects of like, oh, how do you do DMA in this way, and kind of give an example so that your starting point becomes easier. It's just like, oh, when I do something like this, this is where I need to start, and leave all the other stuff to us. Cool, and we'd love to hear what would make your life easier as silicon vendors. Yeah, and I think that's the last slide for me, Sean.
Great, thanks, Anush.
Yeah.
Are there any questions so far about sort of like the non-technical aspects? I'm about to jump into all the gory technical details.
Maybe this is beyond scope or an offline conversation, but if you're giving all this stuff away, what are you charging for? I'm just curious. I'm not a silicon vendor. I'm just like a random PhD student. I'm just curious.
So Nod specifically, our business model is AI software enablement. And like I mentioned, a lot of the folks here on this call we work with, and we enable them. So the enablement component itself is, I consider it like a professional service for us to stand up your silicon. But then we also have an upsell in our code gen search. So if you're not, a large company that has investments in code gen search, or you're not TVM Answer, and you need something for your infrastructure, we can come and demonstrate what we can do. We are in the process of like considering something to have like a basic open source code gen search, so that you can do an open source comparison with like TVM Answer to what we provide. But if you want the bells and whistles of like really drilling into your cost model of your DMA plus how you're shuttling thing, your memory hierarchies, you export that to our search. We abstract it. We have like an analytical model. We have an empirical model. And we can kind of run search, and those are NP hard problems, but we have enough experience over the past years to kind of like apply that to really unlock performance on your side. So the two parts: the professional services for hardware enablement, and then integrating whatever you've enabled into our code gen search if you want it, and if we can prove that we actually bring you value. And if we don't, you have a AI platform and software platform that's kind of enabled, right? So if you're not, if you have any silicon that is not supported by CUDA, we can help you. That's where we are.
And I'd say from the Google side, my interest in this and sponsoring this is making sure that this is a solid component in the ecosystem that can bridge these worlds. PyTorch and MLIR are important, and having those starting points that people can bump into is important. And we're looking to, over time, graduate this more into a community asset, and something that has a broader base of support.
Cool. Thank you.
Cool. Any other questions? If not, Sean, it's all of you.
All right, perfect. We're exactly at the 30-minute mark, so let's dive in. All right, so there's a few parts here. So the first thing I'm going to talk about is the Torch dialect itself. So this is like really the core of the system. And so there was a question before about like, how do you deal with, there's like a million ops? And the answer is that actually Torch has an op registry that's highly systematic about how it describes the kernels. And so, all Torch programs, whether, no matter how you write them, really bottom out in the same set of dispatchable kernels. And those each have sort of a well-specified signature and sort of characteristics such as like do the outputs alias the inputs and things. We have a few hand-defined ops, primarily for the advanced features of Torch script. I have a few examples of that later. And then probably one of the main things also is just the type system modeling for modeling the Torch Python system. Probably the most important thing here is we have a custom tensor type. So there's actually, well, it's really two tensors with a common sort of base class type thing. There's torch.tensor, which is just the general tensor, and then torch.vtensor, which is a value semantic tensor. Obviously, value semantics are nice when you can get them. And so we help to bridge that gap because by default, Torch has, does not have value semantics for tensors. So one other thing that we support here is this unknown data type, element type, which is, again, like it's just an intrinsic aspect of how these are designed, of how the program is modeled. And we started by using the built-in tensor type, but it just gets really wonky when you're dealing with this. You can also do some nice syntax sugar things. There's a few other types which are used to model sort of like, like the dimension fed into a, like which dimension to reduce along, or, like a little coefficient would be like torch.float, like a scalar coefficient. And then lists for like, paddings, strides, dilations, and then dictionaries actually are mostly relevant in the Torch script case. And then also class types are often there, for example, like NN modules. Those are also, we need to model them in Torch script as well. So we have special support for those. So here's an example of like the auto generation. This is our kind of our dump from our script that generates this. This is all just the information we extract from the registry. So there's this signature, a10 : relu. It takes in a tensor, returns a tensor. It has certain arguments, and there's information like, is it mutable or is it var arg, and then we generate some ODS from this. So from this, we actually know that because it's like not mutable, then we can, and it kind of creates a new non-aliased output. We can tag this op as having value semantics, which then guides later transformations that help us to prove, that require proving that a tensor is treated, the non-value semantic aspect of a tensor is not relevant.
Sorry, when you say Torch registry, you mean native functions.yaml, or you mean the registry at runtime?
So we actually use the registry at runtime. The native function, I believe all the information that's in there is systematically derived, like as far as this is concerned, is systematically derived from native functions.yaml. So we could use either, but in practice, we are actually extracting from the registry. And actually, there's one other detail here, which is that the Torch script kind of has its own, it includes all the regular ops plus a set of its own ops, which kind of model this sort of scalar compute-ish sort of aspects, dictionary things, which is actually a superset of the kind of regular what's called the C10 registry. What's this like is C10 op. And so actually we take from the Torch script registry just from a practical perspective because it is like a superset of the regular one. But yes, everything is systematically generated from this.
Thanks.
So here's another example. So if you're familiar with Torch, there's these kind of trailing underscore variants of most ops, which mean that the operation operates in place. So, because it operates in place, obviously something's got to give. And so in this case, this registry hasn't enough information to tell us, for example, that the argument has this alias info. So among other things, we know that it's written to, and we also can join in this alias information to recognize that the return value alias is the input value. I guess it just makes the API more convenient. That the fact that it returns, its input, and so we can actually use this plus to basically know that we cannot mark this op with has value semantics, and additionally, we kind of identify that in our generation script that this is the sort of trailing underscore in place variant, and we set this trait, which then guides later transformations. So speaking of transformations, there's kind of 4 main transformations that are of like kind of top line interest. The reduce op variance will help to smooth over, for example, like relu versus relu underscore. You shouldn't need to care about the different those 2 different things if you don't want to. And then maximize value semantics will turn everything it can into value semantics, which just makes your life easier. And then refine types. This is especially relevant in the Torch script case because like Torch script programs by default don't really know the types of everything. So this lets us propagate annotations on input types through the whole program. And then finally, there's this transformation called Globalized object graph, which so a Torch script program is technically like a Torch script module is actually a module, which is like a graph of objects with methods and things. And so globalized object graph does a whole program transformation, which kind of takes us out of that form and more to a more familiar sort of flat list of globals form. I have some examples of that later. So I'm going to dive in and show these in turn. So here's an example of reduce op variance. So here's like torch.18.10h. So this op has value semantics. It takes in a mutable tensor, it returns another, or just a general tensor, and it returns a tensor, but this tensor is the return is newly allocated and cannot alias the input. And so we know that it's legal to replace this with the bottom code where we take the kind of non-value semantic tensor, copy it into a value semantic tensor, do the operation on the value semantic tensor, and then copy back. So this is a very simple people transformation we can do. And then trailing underscore variance. This is another one. So in this case, add underscore. This dot tensor is actually what's called the overload name, which if you look deeper into how the registry and stuff is structured, you'll see that there's a lot of these sort of overload variants. There can be like 15 of them for a single one. But in this case, this is A plus B times, a little alpha value. And so in this case, this add underscore gets marked with the right and gets transformed into just the regular add. And additionally, this is all happening in the same pass. So it also gets converted to be the value semantic one. So you see here that you get this kind of canonical just add of 2 tensors with an alpha value. That's just how Torch's basic add works. And it's all on value semantic tensors. And then we have some of this stuff around here, like copying, back and forth into value semantic tensors. And then also to model the actual in-place operation, we have an op torch override.tensor, which kind of, we try to canonically, try to lower as much as possible into just that op to make later passes work more easily. So now we have all this gunk. And so, what are we going to do about it? Well, thankfully we have a pass called maximize value semantics. So here's a trivial example. So for example, in this case, the function takes value semantic tensors. And so you can get like a regular non-value semantic tensor, and then you can do things like copying it, doing things, then overriding it, and then getting the value again into a value semantic tensor. And then we just collapse all that into, the look through all that and realize that, oh, there's really no aliasing happening. It's basically like it's almost like an SSA formation type of pass, where you just sort of introduce new SSA values for things. In this case, this all just folds away because they're all identities. But here's another example. So like a view like op, so like an op like unsqueeze view, things like that, flatten. So these all return aliasing views. Actually, sometimes they only sometimes return aliasing views. And so we do all the analysis to look through this and find and prove that there's nothing in the program that relies on that aliasing property, and then turn the whole thing into operating on value semantic tensors. So then you just get these nice, just pure value semantics. So just to give you an idea of like what this reduces the program into eventually after we run the transformations. So like here's just a simple comp layer. We do like a ReLU on the comp, and so as you can see here, basically there's this there's like a value tensor literal, which has the weights, and then we some lists gets constructed for the padding, strides, and dilations. And then we call here the comp 2D, the actual comp 2D op, and then just a ReLU op. So this is all on value semantic tensors. So this is kind of what you want when you're dealing with with the backend. Just as a note, I have it up here. You might be like, oh, why are you creating all these lists and stuff? It's because this is just how like PyTorch semantics are, and we have helpers that let you easily pattern match it into attributes if you need to turn it into an attribute. So that all works really nicely in our experience. Okay, so let's talk about front ends and back ends. So this is sort of the cartoon version of Anush's, the nice one that Anush had. With a few more technical details. So, TorchFX, TorchShape, Lazy Tensor Core, and whatever else PyTorch might come up with, they're all going to boil down into the same source of truth dialect. Again, this is generated from the same Op Registry that everything in PyTorch bottoms out on anyways. So we have a reason to believe that it's highly durable. And additionally, the PyTorch folks do a really amazing job at keeping this registry from churning. So we have been living ahead for months and months, actually like a year or so now, and we have yet to hit a breakage where they, it's like they're like, oh well, instead of comp 2D, we're like our default comp is gonna be like something slightly different or whatever. Like we haven't had to regenerate the dialect or anything like that. So really big kudos to the PyTorch team for keeping things stable in that capacity. And so then, yeah, we have, you can backends, you could lower this to linog on tensors, TOSA, MHLO, or, whatever your heart's desires. You may want to actually piggyback underneath one of these kind of stock conversions, if that's more convenient for you. Yeah, so I'm going to talk. Are there any questions about this slide? All right, I'm going to move on.
There's one on, Sean, there's one on like how are while loops in PyTorch modeled. I don't know if you want to take it now or later.
Yeah, I'll take that later.
Okay.
Yeah, it depends on whether you're using TorchScript or whether you are using something like Lazy Tensor. That's the short answer. In TorchScript, it'll actually generate, an op that is a while loop. in lazy tensor, what you'll get is a traced graph for the unrolled loop, basically. That's the short answer. Front ends. Okay, so right now there's sort of 3 front ends in PyTorch. There's TorchScript, which is a really high fidelity Python subset with a whole program compilation model. I think it was Mustafa was talking about earlier, having that nice deployable artifact. And that's actually where we kind of started from in Torch MLIR back when it was npcomp. And so a lot of work has gone into this TorchScript front end, and it's the most mature right now. We have TorchFX and Lazy Tensor Core, which are being brought up as we speak. So TorchFX is sort of a JAX style symbolic Python level graph tracing, where you can do auto diff and all those fun things. And actually with our Python bindings, we can just write like a pure Python. TorchFX is written entirely at the Python level. We can just import it directly, with our Python bindings. And then Lazy Tensor Core kind of is also tracing based, but it actually intersects below at the sort of device level. And so this is sort of like a seamless under the hood, kind of just plug in your device and we'll trace graphs, give them to you, and you can dispatch them to your compile and dispatch them to your backend, which is especially relevant for a lot of training use cases. So I'm going to talk a little bit more about the TorchScript importer, just because I think it's technically quite interesting, and we put quite a bit of thought into it. So TorchScript is actually a really, really well done IR and runtime representation. Actually, it's very similar to MLIR in the IR like compiler kind of structure. And so actually we can systematically import the entire representation, all ops, et cetera, in like less than 1,000 lines of code. And so there's no like big enumeration of like, oh, here's all the ops or whatnot, because it's the relationship between the sort of Op Registry source of truth and the MLIR dialect is completely systematic. So to Mustafa's point, this, really the great thing is that you can capture the whole program. The bad thing is that you capture the whole program. So if it's, like iterating a list or doing beam search or, doing some lookup in a dictionary or something, then, that becomes a lot harder to support for a backend. But it's doable. Like, for example, in Erie, we can't do that. We can't support that. But yeah, if you just want a graph of tensor ops and you're especially interested in like the training use case where you're running kind of a live session rather than needing to sort of like deploy an artifact somewhere, then it's not the best. And we have some special types to model the Python type ontology, which TorchScript is really well done and is actually like a very clean Python subset. So to give an example of this, so here's like a torch.nn.module. This is the basic building block of any PyTorch program. So here we have some variables. I just initialize this to some dumb thing. And then, you have like a forward method. And so here what you get, like this is like the literal imported IR from this. So actually it's a little bit easier if we start here at the bottom. So like there's this root, you'll notice this is an SSA value at like the top level of the enclosing compilation unit. And so in this case, it's a torch.nn.module, which is sort of like an instance of a class. And then we have, certain slots which model the members of that class for that instance. So in this case, we like this test module, like if in Python you were to like literally create an instance of this test module, which is like, that's the translation unit when you compile in TorchScript, is you take an instance of the test module and compile it. And so that's why we have to model that here. And so this NN module basically has one member. This instance has one member called a range, which has the value %0, and %0 is a a literal, which is 0, 1, 2, 3, which is what the result of a range is. And then you'll notice that here we give it this type, which is a torch.nin.module of this under torch test module type. And then this actually correlates with this declaration that we have here of the class type torch test module. And then this is sort of like a declaration, kind of like saying like struct in C++ or class. And so here we, this declaration specifies that we expect one attribute called a range, which is of tensor type, and then there's a method called forward, and then here's the function. And so and then the function here is exactly what you would expect when looking at this function. Like in the Python, you take the self argument, which is this arg0, get the attribute a range out of it, and then multiply the second argument by that value. So that is like I have to really hand it to the PyTorch torch script folks for just how nicely modeled this is. And then and so then we have this, that's this representation is really difficult to deal with, right? It's like a get attr of, a self argument, but it's like, is this mutated somewhere else? How can I, do anything with this? It's actually really hard to do with this representation because like, you don't really know anything about anything because it's just like a bunch of objects and you're getting attributes, setting attributes randomly throughout the program, and you can reach into parent objects or other sorts of stuff. So we have this transformation called globalized object graph, which turns this into like a flat list of globals, which we represent with this global slot op. And so basically what it turns is all this like root mod, we identify sort of the root module, and then we kind of walk down it and generate and kind of flatten all the methods into like a flat list of functions, and then all the instance all the instance variables into a flat list of global slots. So this is actually a somewhat complicated transformation, but the resulting IR is like really easy to analyze. So you can just be like, yeah, well, a range, can I delete that? Well, I just see if there are any symbol uses at all. Or, oh, is it read only? Well, then I just look at all the symbol uses and it's like, are they read only? So this is not trivial on the previous on the kind of naive or like the original representation, because, this method might be called from multiple instances, for example. And so, this arg0 might be a different instance in each case. So this just flattens it and makes it really easy to analyze. All right, let's talk about backends. Okay, so probably the big thing everyone wants is interop with the built-in tensor type. And so the good thing is that the value tensor type converts trivially to the built-in tensor type if you know the element type. And so we have a bunch of type converter setup stuff that just makes that all magically work. We have a lowering kind of to linog on tensors. So this serves as both a kind of a reference vehicle, because we can kind of run it with on the execution engine with a few hacky things that we do. Yeah, basically there's the whole bufferization story is a little interesting, but anyway, we just bufferize that and run it. But you could also feed this linog on tensors output into Erie. And so the good thing is we've been pretty principled here. We came from a background where we saw this transition from sort of like the NumPy level of abstraction, where kind of ops can throw error, can like have errors that they can do, and have to be like safely handled. They can't just like format your hard drive. Going from that safe NumPy level abstraction down to like raw loops or things that will eventually get lowered down to raw loops like linalg or like MHLO, or actually I'm not sure if it's defined well for TOSA. But basically, we insert the runtime error guards to make sure that like if your k-dimension mismatches on a matmul, then the program will abort safely, and it's not going to just randomly scribble over memory. And it's all these lowerings are also 100% dynamic, shape aware, subject to a statically known rank. So that's just an inherent restriction of lowering to Linux, and most other things at this level is needing to know the rank. And so yeah, but other like the everything's agnostic to the actual extent of the or size of the individual dimensions. Yeah, so this lowering has been working really well. It's just a matter of adding like another directory and lib conversion to lower to TOSA or mhlow. Happy to accept contributions for that. And we have a dialect also that helps. It has like the type of materializations and everything for doing it. We do have this like hacky reference flow that just sort of bufferizes Linux on tensors and uses some crazy C types plus Python bound execution engine to do this, but you can plug any backend that supports Linux on tensors. So that could be Erie, for example.
Sean, just a quick time check. We have like 4 minutes.
Yes. Yeah. Yeah, I think this is like the last 2 slides. So yeah, so this is the comp2d example for Linux on tensors. I'm just going to highlight here is like you basically get a linux.comp2d op and then a Linux generic that does a ReLU. So, basically you get exactly what you want here. We also have an end-to-end testing framework. I'm going to just go over this really fast. You just like literally like 100-line Python file to plug in your your compiler and runtime. We can support complex flows like running on prototype hardware to device lab. And when things don't go as expected, we handle all the errors and diagnose what went wrong nicely, so you can quickly drill down and debug and repro issues. Yeah, so I don't know if you want to do the demos. Probably questions are more interesting at this point. So let's take any questions.
I think we can just
happy to also sync with anybody offline with respect to any of this work. Please reach out on the on these communication channels.
Sean, if you want, we can, while we take questions, you can just bring up the demo too if there are questions.
Okay, yeah, sure.
Can you talk a little bit about this bufferization thing? I don't know if you discussed this and I missed it.
Yeah, no, I don't really want to talk about that here. It's sort of its own fairly gnarly topic, and it's not really substantial to the actual Torch MLIR project. It just happens to be an implementation detail of one of the backends.
Okay, more on topic then. You said that like a test module is a compilation unit. Do you trace? I mean, so there are 2 ways to produce Torch script IR, right? You can trace a model or you can do script analysis. Which of those 2 paths do you use to transform specifications that are actually in PyTorch?
So you can use either one. We accept we directly convert the Torch scripted module instance itself.
Cool. Thank you.
Muthu had a question. Oh, he's left the meeting. Okay.
Robert?
I'm just curious, what does versioning look like for this? Like, is it just going to be kind of kept in sync with the head of PyTorch, or are you going to tag different releases, or what's
right now we're living at head, but I think we can eventually have a story where it works across various PyTorch versions as well.
Cool.
So the good thing is that especially Torch script is compatible across PyTorch versions. Surprisingly, like very compatible, and so you can kind of carry that across versions easily and import it. Do we have another hand raised?
Did we adequately cover the inference topic that was brought up earlier? And we're about out of time, but
I think that was Mustafa.
Yeah, I think that there are probably some follow-up. Maybe we can do that in on the Discord but yeah, I understand the direction. Thanks.
Cool.
Yeah, Discord or discourse. Happy to follow up.
Yeah, so I think the changes with respect to npcomp versus Torch MLIR, actually a lot of it, most of it involved deleting code or things that like incidentally had dependencies that we didn't care about or were too experimental.
Yeah, kind of, and then moving everything up to the top level and making it focused and obvious what it was.
We've had 100 people over the full hour, which is good. Thank you all for taking the time. Any other questions? If not, please follow up on Discourse or Discord.
Awesome.
All right, great. Thanks everybody for attending.
Thank you.
Thank you.